Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Yep.
So it's my pleasure to introduce Sriram Krishnamurthy, who's visiting today for Simon's CAS workshop, but has kindly offered to give a talk on his work on JavaScript. So I think for many programming language researchers, JavaScript is a bit of a kind of figure of fun. Well, last time I saw Sriram talk about JavaScript, I found myself actually respecting the language to a certain extent.
Oh my goodness!
So are you gonna
that talk didn't work at all? Then I have to work. Yeah, I have to work that again. Yeah.
So, and as recent developments have shown, I think we need to take JavaScript quite seriously, especially as it's forming part of our strategy at Microsoft. So Sriram's going to tell us how to make it safe, I think.
Well,
thank you.
Thank you. Thanks for having me here. Thanks for coming despite the Milner workshop. So that's tough competition. And so we all know JavaScript. We've all seen a mashup or two on the web. Here's the most famous mashup. It's the one that introduced the word mashup into our vocabulary. It's from a mashup of Craigslist and Google Maps, and it's called housingmaps.com. Very famous, big splashy thing on the web. And said it was the start of a mashup revolution. You all use mashups on a daily basis, yes? Or no, perhaps not. So perhaps the revolution is not here yet, or perhaps we don't know. So if you're a university professor in the US, you're required to read the house rag, which is the New York Times. Now, the New York Times is the very opposite of a mashup, right? Because a mashup is just combining data from random places and putting them together. New York Times is trying to be an authoritative, that would like to be. Where's the mashup here? Yeah, so all of those ads. And if you're like me, if you obsessively read the source of pages rather than what's actually on them, you see that it says that this is getting content from pix04.revsci.net. And if you go to revsci.net, it's called Audience Science, and it even gives you a little periodic table of users. So you can guess that maybe your privacy is not in their best interests, right? If you go to the opposite end of the world, here's newzealandherald.co.nz, which is a terrible newspaper, but it's their newspaper. And if you look at their sources, there's ad content coming from all over the place. In particular, there's this thing from amgdgt.com. And there's the source. Well, that doesn't have a privacy policy. www.amgdgt.com doesn't even exist. And if you go to the ad server, geeks will recognize that as a server whose homepage has not yet been configured. So, that's the state of content coming in on the web these days. And all the stuff is being put together on a web page. Now, why does this matter? Because it matters because you go to some host that you presumably trust or want to do business with, and this host is sending down a web page to you, which seems innocent enough, except this web page is pulling in data from all sorts of other places, such as ad servers, but it's not only about ads, which so far still looks good. I have a blue box and a red box. Unfortunately, there are no blue and red boxes on the internet. In your browser, there is a box. And all these things run with everybody else's privilege. In other words, we're back to Windows 3.1. which even Microsoft can tell you now is a mistake, right? So that's the execution model of the web. So what can these malicious programs do from third-party content? Well, here's one thing they could do. They could write this line of code in JavaScript called window.location. And what that does is effectively takes that string. It's as if you put it in your URL bar and hit enter. Okay? Now, the thing about web content is, you don't actually know what's happening in the world. Right? There's a page that says the following things happened, and maybe that's the truth, and maybe it's not, and maybe that's what the New York Times is really reporting, or maybe not. But maybe you're like me and you obsessively look at URL bars, so you wouldn't fall for a trick like this. But instead, here's a different piece of code.
It puts that in the URL, and you then hit refresh when you go there.
You don't even have to hit refresh. The point is, this is as if you put it and hit enter automatically. So it automatically redirects you. It's a redirect, that's right. Right. Except the URL bar looks now different, right? So if you pay attention, you would notice I'm actually at, bankofamerica.com or something like that. Okay? But here's something a little more subtle, which is you can go through. So this is the power of JavaScript being exploited. Right? JavaScript makes it very easy to find all the elements on the page that have the A tag, which is, in other words, links. And now you can rewrite all of those A tags to instead go through some tracker that's tracking what articles you're reading or what you're doing or something else. And it might even be that this ad.com then redirects you to the actual news page, so you don't even realize that you've gone through some intermediary that's tracking your behavior. Now, if you look at this, you'd say, well, it's pretty obvious, right? We should just statically reject these pages. Why is somebody being allowed to write to window.location? Why is somebody allowed to write to document? So let's just reject all of those things statically. But of course, this is JavaScript, which means you have this wonderful property feature called eval. And this is the interesting thing about eval. I mean, eval is a programming language feature that always elicits some reaction or the other from a crowd. The real problem with eval is no matter what static guarantees you erect for your program, there is a dynamic backdoor around those static guarantees that the static checker never got to see. There's parts of your program it never got to see. That's the real problem with eval. Question?
Is eval actually used a lot in the mashups that you have?
Some. There's actually been a pretty good study of this by Gregor Richards, and he's a Jan Vitek student, with the predictable title, The Eval That Men Do. And I seem to remember their findings were about 80% of it could have been rewritten to be much less harmful. You could have gotten rid of all the ugliness. But about 20% of it, the code patterns, people, it's what you expect, right? Random.
The only idea that comes to mind is just disable using eval in your browser.
Yeah. So something that's clearly what you need to do, right? It would be pretty harmless to get rid of eval. Yeah, it would be. When I say harmless, it would be. It would not be a major intrusion on programmers' freedoms to get rid of eval, and it would be a good thing. Okay. All right. So that's the real problem with eval. And so then, of course, there's, it's JavaScript, so it's obvious what this is, right? This is window.location. And there's actually a website that will convert any JavaScript code into something that uses these strings for you. It's, the usual amusement. OK, so this is the kind of thing that your ad could be doing. So this is the kind of red code that could be running with the blue code's privileges. Okay? It could also be talking back to the host server. It could be talking back to the New York Times or to the Facebook server. Okay? So here's the kind of thing it can do, and this chunk of code I'm going to go through in steps. So there's an operation called window.xml HTTP request, which is basically a way of saying, please connect me back to the server that I came from. So connect me back to the blue server. Okay? And this is a mouthful, so I'll just call it XHR, as all people on the internet do. Now this is a kind of important JavaScript detail. And this is where JavaScript, even though it claims to be an object-oriented language, behaves very differently than traditional object-oriented languages do, as does Python, as does Ruby, as does Lua. So every modern scripting language has this feature or bug, which is that when you write something like O.f, you mean a static dereference of the first order name f. But it's actually purely syntactic sugar for turn f into a string and look it up dynamically in this big array of properties that O has. And there are some wonderful bugs that you can discover in this way. You can, for example, use this kind of thing to. We locked up Google Docs, for example, using this feature because of this problem that something is both a dictionary and an object, and it's in certain contexts you can confuse it from thinking one is the other. Okay, so this is just a underlying reality of JavaScript code, and this is a difference from, say, Java. Almost.
What's the difference here? So O.f means go and find the f method in object code.
Oh, the f member, yeah.
F member, right. So how's it going to do that? It's going to look for f in some table, isn't that? It's the second thing. So you're making a distinction there, I don't know.
Yeah, I am, because the thing is, the thing in double quotes could be a generated string. It could be a calculated string.
Oh, okay.
Because it's a string.
You can call a method whose name you make up on the fly.
That's right.
It's a bit like a val.
Yeah, a little bit like a val.
So
Yeah.
a val string.
Effective, sort of, yeah.
So it's like an eval.
Yeah, of the member's name. It's a very specialized eval, yes. Okay? So when I say window.xhr, what I'm really operating on is I'm calling window of this string. Okay? So here's the kind of thing that this malicious code could do. It could create one of these objects, and if it happens to know where some method resides on the server, it could actually invoke that method. So it could, if it knew that the privacy settings are behind the URL set privacy, it could send a message there and change your privacy settings.
The details
Yeah.
Detail that you stress is not important for the
Not yet.
Okay.
Not yet. But it's a good setup for something that will happen in a little while. Okay? Good. But not for this particular example now. Okay. All right. So people have known about this for a long time. In 1998, Hotmail introduced this wonderful feature, which is you could put HTML in your messages, which meant you could put JavaScript in your messages. And in about 2 days, you had messages like this, Hotmail open to attacks, which of course explains why in 2010 this is now a feature. It's the same thing, by the way.
So what was the attack?
The attack is I can put JavaScript inside my email message to you, which then goes off and does whatever evil thing. I forget which particular evil thing this attack did. But the point is you're expecting
You said something to do with talking to the server.
It could be changing things on your page. It could also be talking to the server. Okay? The point is you expected your email message to be inert.
Okay.
At best, you expected it to have some local reactivity, maybe a little spinny thing in there.
This is not immediately connected to your previous slide. This is just saying if you have HTML and email,
then you have these problems, right? But now you can actually do it. And it's considered a feature. It's they forgot that they introduced it about 12 years ago. So what changed? Well, one of the things that's changed is people are now aware of some of these problems, and there are now commercial solutions to these problems. Facebook, for example, critically needs solutions to these problems because Facebook depends very much on you being able to put Farmville inside your Facebook page. This is the business model of both Zynga and Facebook. But if you look at their filings, both of them are deeply antagonistic to the other, right? They sort of tolerate each other for their purposes, but they're both antagonistic, and neither one wants the other one to be able to come in and do something malicious to their users, right? So Facebook certainly doesn't want to let Zynga be able to modify your Facebook settings and vice versa. So Facebook needs this kind of solution. Yahoo needs this kind of solution. Google needs this kind of solution. So a lot of companies have gotten into the business of trying to define sandboxing solutions for JavaScript, which is basically, I drew you this virtual picture of this blue box and this red box. Let's keep the blue and red boxes as red and blue boxes, okay, and not have them merge together. That's what a sandbox is trying to do. But if I wear my PL researcher hat, of course I see this as a different thing they're trying to do, which is they're saying JavaScript and it's not just JavaScript, right? It's this environment that JavaScript runs in. This environment is too powerful a programming language, and what we want to do is define a sub-language of it that is still effective for people to write programs in, but much safer. Okay? And so now this is a PL problem. This is our business. Okay. The Kaha team, and just to give you a point to some of the difficulties here, these are large collections of semi-ad hoc JavaScript, these sandboxes. So the Kaha team actually brought in an external security review team, and they said wonderful things about it, and Kaha is a very, very clever product, but they also said Kaha is very hard to review. There's no map that states what the invariants are and points to where they're enforced, which of course hurts maintainability and security. Now, of course, I read this kind of text and I think, you're saying there are no types, right? So this is this.
What is Kaha?
Kaha is a solution to sandboxing. Okay. And I'm going to talk quite a bit more about sandboxes, so it's just a name for now. It's a Google product that's very good, but has this problem that people identified. And AdSafe is Yahoo's proposed solution. And if you look at, when AdSafe was released, this is the message that went out. I need your help in testing its robustness. Are the rules sufficient, et cetera, et cetera, et cetera. And essentially it ends with, if the program produces no errors under this condition, I will buy you a plate of shrimp. So if you can break it, I'll buy you a plate of shrimp. Security by shrimp. Okay? So perhaps a better name for AdSafe is AdSafe. Okay? And that's the question mark we'd like to get rid of. Okay. So let me give you a high-level overview of the structure of these sandboxing solutions. There are lots of technical differences between them, but it's, from 30,000 feet, they're all the same, which is the following. The first is they are going to statically reject things that will destroy any invariants, like eval. And I have ... there because there's other eval-like things, not the field dereference, but other things that give you the full power of eval. So those, if it sees them in the program, it's just going to say, sorry, I'm not going to let this program go through. But the problem is there's a lot of things that are only conditionally bad. So if you dereference XHR, that may be a problem, but if you dereference some other string, that could be just fine. So those are conditional things. So it rewrites them into guarded operations. Okay? And these guarded operations are going to come from some trusted server. Okay? So those are wrappers that are going to check whether you're using lookup in a bad way. If you are, they're going to terminate execution or something like that. If not, they'll let you continue. Okay? So this paradigm of checks, wraps, and rewriting is a sort of standard terminology in the web sandboxing literature. But it's always good to step back a little bit and never mind, the web, blah, blah, blah. There's a much older name for this, which is these are reference monitors. And if you go back to the original paper that introduced the term reference monitor, which is, I believe, a MITRE tech report from 1972, it's a gem of a paper, and the person who wrote it pointed out what the properties are that a reference monitor should have for its verification. The first is it should be tamper resistant, because one way to break this is I just break into the New York Times server and produce, stick a lookup function that allows evil things to happen. The second is it has to always be invoked, pretty obviously, right? That's the reference monitor part. And the third is it shouldn't be circumventable. I'll tell you in a moment what circumventable means. So let me give you a very simple lookup function, okay? So I want to guard against you being able to access the XHR method. That's the guard I want to perform. And I'm actually exploiting the fact that the field name is a string, right? I can basically do my metaprogramming in the language itself, because I turned it into this function call where the field value became a string. And so I have this function that takes an object, takes a field name. If the field name is the string XHR, I slap you on the wrist. Otherwise, I let this to operate. Right? So far, so good? Very, very simple reference monitor. Right? Some of them will rewrite it for you. Others will expect you to have rewritten it yourself. So if you put brackets, if you write the bracket in there, it'll statically reject it, saying you should have written lookup instead. That's an implementational difference. Okay? Assume that the rewriting was done by machine or man. Okay? Okay. So here's your reference monitor. It's obvious to everyone that this is buggy, right?
Could I write an escape in XHR?
Well, actually, here's what you can do. In JavaScript, since JavaScript wants to be maximally permissive, if the field name is an actual string, it will look up the string, but the field name can be all sorts of other things. In particular, the field name could itself be an object. And if it's an object, it invokes the toString method of that object. And so if I call lookup with an object that consists of a toString method, now my lookup has been subverted to do exactly the thing that I'm trying to prevent. Okay, so there's my second argument, and so lookup is in fact unsafe. So this is an example of circumventing, right? I'm sending a nasty payload that makes the reference monitor do the nasty thing that it was designed to prevent. Okay? Very simple example. And part of the messiness of JavaScript, this is just sort of reality of the browser, is there are lots of other evals in the world.
Wait, I'm sure they believe this, because before you said that, so in the conditional would say that fd is equal to XHR, so fd is an object. Okay, so that equals doesn't have the same semantics as the lookup. You just need the equals to have the same semantics.
Yeah. Okay. Good. So there are other evals in the world. So here is something called SetTimeout. SetTimeout is basically, it's a way of telling the cooperative multitasker, put this in the queue, and when the timer elapses, please call this function. Okay? So 1,000 milliseconds in the future, please run the function f. But it would be hugely onerous to expect people to create functions. So in fact, you can actually write a string there instead, which of course means that's an eval, right? It converts any JavaScript string you want into a piece of executable code. So you have to look out for these other things as well. So here's the structure of ADSafe. I've given you a high-level overview of how it works. And there's lots of entry points. There's these DOM calls that you need to check for. There's various assertions, type tests, regular expressions. So it's a chunk of messy code. And that's what we want to set out to verify.
Do not do these things.
It has both blacklists and whitelists. Yeah, so the structure is, but in particular, it has blacklists that you want to check for. Okay? Okay, so this is the same picture I showed you before. JSlint is the name of the static checker. It's a lint checker for JavaScript that happens to have an option that says, please perform some additional checks because I'm going to run this with ADSafe. So I have JSlint, and JSlint will reject things like eval. It's like a code smell tester for JavaScript. And things that pass JSlint are going to be linked against this ADSafe reference library, right? That's the reference monitor. And so this is what we want to verify. Now, what does it mean to verify? because if you go to the ADSafe homepage, it doesn't actually list any properties or anything like that. So we went out and spent about a month reading the code, trying to figure out what properties it might have, sent them off to the developers and said, these are what we believe to be the properties. And they wrote back and said, yes, and here's one more. So here are the properties. So the assumption is that you've passed JSlint, you've passed the static check. Okay? If you pass the static check, you can't load new code at runtime, essentially no eval or eval-like things.
So if you pass the static check and you link against the...
Yeah, yes, right. That's right. So no evals. Widgets can't obtain direct references to DOM nodes. The DOM is the data structure. It's a reflection of the web page structure into a data type in JavaScript. It's kind of the power of JavaScript. It's this reactive data type. You can read it, and it's sort of a live datum. If you write to it, the web page automatically changes. That's all very nice. The problem is that the DOM happens to not be a tree. It's actually a graph, and it has evals and things like that sitting in it. So you really don't want to give the DOM itself. You want to have this mediation to the DOM. Okay? So ADSafe is going to define something called a bunch, which is a gentle version of the DOM, and you don't want people to get direct references to the DOM. Okay? Widgets shouldn't affect the DOM outside their subtree either, right? There's this expectation that I'm going to give you this chunk on the page to put your ad or Farmville or whatever content in, and you shouldn't go traipsing off from there to alter the news headlines or the Facebook status and so forth. Okay? And finally, multiple widgets on the same page can't communicate. So ADSafe gives you some mechanism whereby widgets can talk, so it can also turn them off, and you shouldn't be talking to each other directly. Okay? This is the properties. We'll see at the end how well we do. This is the properties we're trying to verify. Okay. Let me give you a sense of how this actually works in these sandboxing systems. We have this property that says widgets can't obtain direct references to DOM nodes. So first of all, JSlint is going to make sure that you can't get direct references. It's going to look for, it's all four-letter words, like eval, node. These are all four-letter words, and it's checking a whole bunch of bad words. Okay? So it says if you try to do...
Bad method calls. Wow.
Yes, exactly. So
those operations that would return.
Yeah, so that's a subtlety. Okay? We'll get there. So first it's going to just check for direct references to bad words.
Well, there's some global variables.
Yeah, globals that you shouldn't be getting access to. Yeah, exactly. Slash, yeah. Okay? So that's trivial. It's only going to let the word bunch through. It's not going to let the word node through. ADSafe is then going to ensure somehow, hopefully, that it only permitted safe methods in this bunch collection. So bunch is a new data type, and it's got a reference to the actual node, right, the actual DOM, and it provides these things like append and get text, and these are meant to be sanitized pieces of code. Okay? Now, nodes is sitting there, and it's kind of public because JavaScript is, of course, a scripting language, so you can't have private declarations and things like that. That would be too sophisticated. So JSlint makes sure that you can't say nodes either. That's another kind of bad word. So it's basically making it a private field. And then ADSafe is going to hopefully make sure that things like append don't return the DOM. Hopefully, right? It hopefully returns a bunch rather than the DOM, but you have to worry that the code might itself be broken, or maybe there's a subversive payload that can cause it to return something you don't want. Okay? So this is the kind of subtlety that you have to, this is sort of the reasoning that goes on to make sure that this program is actually doing the right thing.
But the append is part of the blue code on the left.
Yes, that's right. Sorry? It's trusted code. Well, so the thing is, the point of showing you that little lookup example I showed you is that you shouldn't trust the trusted code. Right.
Check the trusted code.
That's right. Right. So, okay, so we want to verify this system, and what we are after is verifying ADSafe. We want to check the code of ADSafe to make sure it can't be subverted. But remember, ADSafe is running with the expectation that JSlint has already run. Right? In fact, the ADSafe code on its own almost certainly will fail to verify if you don't encode the assumptions of JSlint somehow, right? Because there's just too many attack surfaces. So we need to do two things. We need to first model JSlint, and then we need to verify ADSafe against that modeling. So the way we chose to model JSlint is through static types. So we're going to try to construct a static type that represents the set of allowed behaviors of code that passes JSlint. So what are you allowed to do in JSlint? Well, so I'm going to define this type called widget. So you're allowed to declare, constants. Constants are fine. They're basically harmless. So the widget type lets you write down, numbers and booleans and strings and so forth. Okay. You're allowed to define objects. Okay. But some fields of some objects are not good. So this name arguments is a bad name because once you have arguments, it turns out it's another way of getting eval. Okay? So you're allowed to write objects. Notice I'm defining a recursive type here. So star means all fields except those explicitly enumerated. And things like arguments and caller and a handful of other names, the blacklist, are marked with this little skull and crossbones. In the technical development, the skull and crossbones is basically a type that has no elimination forms. Okay? So you can't wipe them out. So you can't actually construct a type judgment tree. So that's what they are. So think of them as if you touch this, the type checker blows up. Okay? So you can't write those. You're obviously allowed to write functions, but the functions have to consume safe values and return safe values. So they're all widget to widget, and the dot 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 is saying they can have any number of widget typed arguments, but they have to return widget type values. Okay? And finally, you're allowed to do a certain handful of harmless things like creating arrays and regular expressions and so on. Okay? So there's a type that's about 25 lines long that represents what we claim are the allowed behaviors of JSlint. Okay? This is a type we constructed by sitting there and writing lots of programs and studying several programs, and this is our claim about its intended behavior. Okay? Beg your pardon? Some of those ended up in the skull and crossbones.
But only what things called arguments. The only skull and crossbones here is arguments.
No, there's a dot dot dot. There's about 20 other things there.
Oh, I see.
Including eval. Yeah.
Okay, so all the bad words are in there.
All the bad words are in there, and you'll see a little more of bad word modeling in a moment. Okay? Good. Question? No? Okay. Stretching. Good. Okay. So this type, we claim, represents what JSlint is trying to allow. Now, a 25-line type is kind of a messy thing, but it's a heck of a lot better than several thousand lines of ad hoc JavaScript code that is claiming to represent a static checker of programs. Now, the question, of course, is how does this type compare to what reality is doing?
So isn't it the same as, we can simplify this by saying, recursively, no bad words?
Yeah.
Isn't that what that type is saying?
Yeah.
Only 25 lines to say that. You can say it in 5 words. Recursively, no bad words. And here's the bad word list.
Yeah, there's a little messiness with things like prototypes and so forth. But yeah, that is what we're getting at. Okay. That is effectively what we're. That's what JSlint was doing.
Okay.
Yeah, and we'd like to aspire to do a bit better. Okay. But yes, effectively you could summarize it in those 3 lines. Okay. There's a bunch of things on that last line. Other than that, it's 3 lines. Okay. Good. So now there's a question, which is, I've got my claim about what I think JSlint is doing, and there's something that JSlint is actually doing, right? And what's the relationship between these? We would like the relationship to be the one I've just shown you, which is if the things that pass JSlint are contained within the widget type, then we can just use the widget type for our verification and know that we've covered everything that JSlint is going to let through, right? In fact, if it's a little bigger, that's actually okay, right? And it turned out that this claim was not true. We ran it against the test suite of ADSafe. So when I say 1,100 lines of code, it's actually about 1,100 tests. And we ran it against the test suite, and it failed a few times. This claim did not hold. And every single one of those failures was converted into a security attack. So the problem...
Test suite.
Sorry?
Their own test suite.
No. They passed their test suite. But this claim was run over the test suite. So what we're doing is we're testing our programs against their test suite. Our type checker against their test suite, right, with this type. And the reality is when you write a grep-like program, you don't write a proper recursive descent program, which means you miss corner cases. And since we have a type checker, we catch the corner cases. So now it is true. This containment now holds. Right? We sort of found all the things that were sticking out and found that we could turn them into attacks. And once you get rid of those attacks, the corners actually, the circles fit. Okay? And the other thing to note here is that passing this containment is actually means that you could get rid of JSlint entirely and just use our type checker as the front end, right? So you don't have to, but you could do that. And you'd actually be able to run more widgets in that case. All right. So we're going to use this type to model claims about about JSlint. Now, I'm talking about types for JavaScript. Where do these come from? These are actually Arjun's thesis. So, for example, it has untagged unions in the type language. It's got this notion of blacklisting. It has prototypes rather than classes because that's what JavaScript has underneath. And it also has these field patterns, which are actually, they could be any decidable language, but they happen to be regular expressions, because we have to take into account this fact that field names are actually strings. They're not actually first order field names. Okay? So you can encode some of the field name structure in the type of objects. Okay? So there are two key features. One is this thing that I just said, which is that field names are strings. The other one is this thing that you can do, which is type refinement through control flow discrimination, and I'll show you that in just a few moments. Okay? So now we're ready to verify ADSafe. What does that mean? We have the ADSafe library, and we've got some widget. We don't know what the widget is, right? We're trying to verify this for all widgets that pass a particular type. What we know about the widget is no matter how complicated it is and what communication is happening inside, all that communication is widget typed. That much we know, right? Everything is recursively widget. Okay. When it calls into ADSafe then, it must be the case that it's sending widget type values. And we want to make sure that ADSafe is also returning widget type values. Except, of course, ADSafe, someone has to do the actual work, right? The reference monitor is the thing that has the reference to whatever harmful operations are there. And so it might be talking to things like HTML elements and modifying the web page. So the critical thing is that widget and HTML element are not in a subtyping relationship. So you can do widget HTML element type things over here just so long as you don't return any references to the caller. Okay? And similarly, there's this SetTimeout thing, which is also, I told you, a kind of eval. And that one we'll investigate in a moment. So again, we've got these widget type things coming in, and we want to make sure only widget type things go back out. That's the thing that enables us to do the security reasoning about the properties that I mentioned. Okay? So we have to type check ADSafe. We have a type checker that has explicit type annotations. So we have to put annotations on, but it's actually very easy to infer the types because the types we infer are everything consumes a set of widgets and returns a widget. Right? That's our type annotation. A little script does that for us, and then we go off and run the program. And so some of the evil things, like I told you there's this other eval, which is in SetTimeout. The way we record that is in the type environment, which I've glossed over until now. Right? I've got this huge DOM, and I need a type environment for it. So we go through the IDL files and generate an initial a type environment, and then we go in and refine the type environment in places where bad things could happen. So notice that SetTimeout was one of these things that could either take a function or take a string. I have written my type to prevent it from taking the string argument. It has to take an explicit function argument. Right? So I'm blocking the eval case of SetTimeout through that type environment.
For the external API of the ADSafe library?
Yeah, for the browser. It's for the browser API.
In your picture,
yeah.
The blue code.
Yes.
It's the external API, not all the internal functions.
That's right. That's right. Exactly.
So you're writing the API for the blue part.
Exactly. Okay. So here is an example of bad code. So ADSafe exports SetTimeout under the name later, and later takes a callback and a unit of time, and it calls SetTimeout on callback in that unit of time. Okay? Well, except of course this is bad code because there's nothing here that prevents me from sending a string, because widgets are strings are widgets, so I could send a string in and I can get the eval behavior. So this is not the actual ADSafe code. And if you tried to type check this piece of code, you would get a type error because there's nothing that says the callback argument must be a function. Right? It could be the much bigger widget type, not just the function part of it. Okay? So the actual code inside ADSafe looks like this. It says if type of callback equals function, type off in JavaScript is a misnomer. It should really be tag off because it's checking the runtime tag. Okay? So it's saying if the thing that I got in is an honest to goodness closure, then you can pass it to SetTimeout. Otherwise, error or something else. Okay? Yes?
That's still not good enough. It's not sharing the types of the arguments you return value.
Come again, please?
It's just saying it's a function, but you only want to use it for functions taking widgets and returning widgets.
Right. Okay, good point. So the reasoning here is this runtime check is only ensuring that I have an arrow type. Okay? But my widget type, the only kinds of arrow types it permits are widget arrow widgets in that big recursive type. Okay? And so in fact, that is precisely the thing that's interesting here, which is if you think about the type of callback as declared at the top. I've declared it to be of type widget, right? So in a traditional type checking context, when I try to type check that call to SetTimeout, it's still of type widget, right? I mean, there's an if statement above it, but it's still of type widget. So this ought to fail for the same reason the previous code failed. But in fact, what type JavaScript does is it takes these type checks into account, these tag checks into account, and narrows the type based on the supposedly dynamic checks that were performed, so that that line there that says if it's equal to function picks out of this big union type, it picks out the line that says you must be the arrow type. Since
and what if this condition was inside the function code? What if this if type was, it would go inside that?
There's more complications than that, which is there's a whole bunch of control operators in JavaScript, right? It's a small language, so obviously it has only about 10 different ways of doing these kinds of tests. And people use all of these to greater or lesser extents. We've also studied code bases in Python and Ruby, and we find the same behavior in Python and Ruby where people use tag tests to do type discrimination. So the interesting thing in type JavaScript is it actually uses a combination of flow analysis and type checking to perform this kind of type refinement. And it's technically quite interesting because so the progress and preservation are only achieved through the union of them. One of them does not satisfy progress, the other one does not satisfy preservation, but you compose them together and the theorems prove that you actually get progress and preservation out of the composition. So there's a little bit of technical innovation going on to make this work out, and that's how we handle those kinds of cases. Question there and then there.
So you said that strings are widgets. So what if that function was like a two-string type of?
Strings are widgets, so yeah. So what if the the point is the two-string case was I had to pass in an object, right? And if I passed in an object, that would not pass the type-off check over here. So if I sent in a malicious object that had a two-string in it, the top-level thing I would be sending in still is an object and not a string or a function. Could you construct? Well, you presumably could, but then the function could not truly be malicious because it would have to be type widget to widget, right? Because if I allowed you to pass an object into SetTimeout, then I could construct the function in such a way that the type checker, that the JSlint would not be able to see it, right? But because I'm only allowing you to pass in functions here, that function must be something that JSlint got a chance to examine and blessed as being widget to widget, and our assumption is that widget to widget is not harmful. Okay? So that's the line of reasoning here. Good catch. There was somebody else? Yeah. Well, so it's very much inspired by that. In some sense, what happened was we looked carefully at the occurrence typing rules and noticed that what was really going on, in our mind anyway, was it was an encoding of a transfer function in a data flow. So we said, well, why not just make it a transfer function in data flow? And there's actually I don't know if this is the right time to talk about it. I'll say something interesting about that later on, about spines. Ask me about spines at the end, okay? Okay, so anyway, so that's the thing that makes this kind of, so this is what enables us to type check a bunch of legacy code that was written without type JavaScript in mind, using the type tag tests that programmers in JavaScript are already performing. So here's an example of an actual piece of code, and type checking it gives this error. What's going on here is, let me see. So I have this URL, which I'm using as a regular expression, and I'm testing whether its value passes whatever this test criterion is. And I'm then later on using the value over here. I'm assigning it over here. And the problem is the way you attack this code is you pass in a function, you pass in a value, an object that actually has state in it. And so the first time it will pass the URL test, because it basically records how many times it's been invoked. It says the first time I was invoked, I'm going to return an innocent string. It'll pass the URL test over there. The second time it's invoked in a two-string, it will eventually produce the malicious thing, right? And so the type checker notices, basically here the type checker is not giving us the counterexample that says, here's how you attack it. What it's saying is, I am unable to statically prove that this thing is safe, right? The construction.
Where is the test failure? There's no location here. So
In the red, do you see the red line there?
yes. Test, it expects a string, which is the value.
Yeah, but I got a widget which could be an object, which could have a toString in it, which could be bad.
So where did we see the test needs a string? Is that in the type environment? Why did test expect a string?
That's because yes, that is in the type environment that regular expression tests should be given strings.
Oh, okay.
Right. Okay. Yeah. And if you write the appropriate test or check around it, it actually blesses it in this case. So we found some actual errors. We found JavaScript execution errors that could be hijacked to cause malicious behavior. In each case, we were able to construct an actual attack on the system. We also found a bunch of, the nice thing about a type checker, of course, I don't need to tell this room, is that type checkers actually improve the quality of your code. So we also found several ways to improve the correctness of the code or the readability of the code, and every single one of the edits we suggested was actually accepted and put into the ADSafe code base, and it's now been a year and a half and nobody's discovered a new attack. That doesn't mean there isn't one, it just means that maybe nobody's checking for attacks, I don't know. So the point is, we've been able to successfully improve a production system using this type-based strategy. So how did we do on these properties? Well, so the first one, well, I'm going to claim success, but to be honest, it's a little bit of a shaky claim because it's really a question of how good our model of the environment was. Right? It could be that we missed something, and really if we wanted to do a proper end-to-end verification story, we ought to be looking at the source of the browsers as well. It's something I've been wanting to do, we just haven't had the resources to do it yet. The bit about obtaining direct references to DOM nodes, which as I've explained can be quite harmful, and it sort of completely destroys the idea of having an add that's in a sandbox, that is achieved through a type-based argument. Right? Even the first one's also a type-based argument, but it's only as good as our modeling. The second one is basically because of this lack of subtyping in either direction. Right? So you don't get this flow of values of nasty things into good things. The bit about affecting the DOM outside their subtree, we have a partial argument for it based on the types. We can't completely construct it based on the types, but it's also less important because the way people achieve this in reality is using something called an iframe, which gives you this kind of sandboxing for free, and it's sort of, you're punting to the operating system level, which is perhaps undesirable to a PL person. But the point is we have a combination of arguments between iframes and the type-based argument that essentially gives it to us. We just can't make the argument entirely based on types. The last one is interesting because we started to think about how we might prove such a thing. This is kind of a non-interference property which our type system was not set up for. So we started to construct we started to investigate the question, and we came up with a type error that we were able to turn into a counterexample to this claim. So we sent it to the developer at Yahoo, and the response was, oh, I can give you much better counterexamples than that. I'm going to retract this property. Which is kind of a scary thing. It says that basically the current structure of our web infrastructure is so bad, it's so leaky, that you essentially can't get a meaningful non-interference property for it. And that's kind of unfortunate.
What are the ways of getting through some global methods?
Through global methods, through writing things to the DOM, there's just all sorts of covert channels of communication that you can't quite pin down. In fact, when I went to give this talk at Google, I started off, I had the same slide at the beginning of the talk, you recall, and I put up these properties, and I got to the fourth property, and the moment I listed the property, Mark Miller jumped out of his chair and says, that's complete nonsense. Where did you get that property from? So I'm beginning to think maybe the property was given just to test us, not because it was actually believed to be a property. So who knows? So it says something unfortunate about the web, that getting some kind of non-interference property seems completely beyond scope with the current technology. So there's a research question, right, defining this in a better way. So anyway, so I started off asking ADSafe, and I'm claiming now ADSafe, except we have about 11 lines of code we haven't been able to verify as of the time of writing this paper. So I'll maybe take a little bit of the claim off. Sorry?
Just look at them.
No, well, so we did that. And not only did we convince ourselves, 6 of the lines have now disappeared in the new version of JavaScript because it's working around a weakness of JavaScript. The other 5 lines we do now know how to type check. So if we felt like it, we could go back and get the 11 off. But the bigger test, of course, is there's the shrimp. In fact, that's Joe and Arjun, and they went to a Doug Crockford to some restaurant in the Bay Area, and Doug ordered all the shrimp dishes available on the menu. So he must have liked what we did. Okay, now I made claims about a type system, and I talked about soundness, progress, preservation. So I'm basically making claims about correctness proofs for JavaScript. How do we do this? Where do we get what do we prove correctness against, right? JavaScript is this language. It's about its definition. It will hurt your foot, right? It's in that category of language. If you drop the manual, you will have to go to the doctor. NHS, I guess. So, of course, we do what academics do, right? We define the essence of JavaScript. And the essence of JavaScript is, Lambda.js. And it fits all on one slide. Well, it's actually, there's one more figure that's missing. But, it sort of fits on a, those URLs, I'm sorry. I should go away. So it kind of fits on a slide, right? It's LNCS. It's about 3 figures that are about this big. So we're done. Well, except that's a little unsatisfying. Yeah, that's the dynamic semantics. That's right. That's right. But even then, there's no reason you should necessarily believe my claims about the dynamic semantics, right? I mean, we've written down.
Including the effect on the DOM and all that?
No, this is the core language. I'll get to the DOM in a little bit. Okay? Yeah. But even, let's just talk about Lambda.js, right? Just the core language. I mean, I've got JavaScript programs. I've got Lambda.js programs. I mean, it's easy to write an interpreter for Lambda.js, right? Every PL student can write one in an afternoon. So we did something that is sort of dangerous as a PL researcher, which is we actually implemented that transformation. So it was about 1,100 lines of Haskell code, which meant we could now take JavaScript programs in the wild and run them through our interpreter, slowly get an answer. And as you might know, there are other evaluators for JavaScript in the world, which means we now have to confront this question of, are these answers the same? So writing down Lambda.js took, I don't know, about a week or two. This process took about 3 months, but we now have identical output for a chunk of the Mozilla JavaScript test suite. And when I say identical, that means, it prints out answers. It says, OK, not OK, OK, not OK. We can run against the Mozilla JavaScript test suite. We run against ours, much slower. And at the end of the day, we get 2 files. We diff them, and the output is empty. Okay? So we have a tested semantics. And I like the fact that it's essentially as tested as the browser, right? It's against the browser's test suites. It also has this nice virtue, which is in the security world, people don't attack specifications. They attack implementations. So being able to say we model the implementation has some real value to it.
Did you discover any bugs in the implementation?
Well, actually, Mozilla doesn't pass its own test suite for amusing reasons. So we didn't need to. They've already put them in there. Yeah. So.
When you say a portion, is it a portion because you could only test the bit that didn't interact with the rest of the world?
Partly that, and partly, grad student effort. 3 months was a good upper bound on it. So actually, there's an interesting footnote to this, which is the new ECMAScript standard. They have made, I think in part because of efforts like this, they have actually provided a conformance suite as part of the standard, which I think is very nice, because instead of trying to bake a semantics into the standard, they've implicitly baked a semantics by baking a conformance suite into the standard that's actually maintained, and all the browser implementers are behind. So our new version of this for the new ECMAScript language is tested, I think, about 80% now against the conformance suite that is provided by the spec writers. Yes?
Last question. So the portion is 50 programs or 500 programs?
This is several thousand. Yeah, it's non-trivial. I mean, this is why we're able to discover subtle bugs. Yeah, otherwise you wouldn't, yeah. Everything but eval. Everything but eval, but we also do width, which is like this incredibly ugly piece of JavaScript thing. Oh, yeah. So we do that. We've got prototypes, like cats and dogs, and you set cat.prototype to dog and dog.prototype to cat and all this other beautiful. Yeah, it's all Lambda.js, yeah. And I mean, of course, Lambda.js is, we say the essence, but there's no reason to call it the essence. It's an essence of JavaScript, right? You could, like Wadler said, you should have put, the prototype lookup into a loop, and then you could have just done that in the Lambda calculus itself. But we felt it was important to provide a calculus that identified what we think are the critical elements of JavaScript. Somebody reading it will get some insight into the language. But at the same time, we threw out scope objects, and we actually made substitution work, because we think that's just a bug, and now the new standard has also concluded it's a bug. So we've had some effect on the standardization process, which is nice. And the nice thing about a tool suite is, of course, now lots of people can use them. So we have several. It's kind of unfortunate all of our competitors are using it now, but I suppose that's a success of a sort. So that's the end of my talk about the verification effort. I wanted to just step back and tell you a little bit about what we're thinking about as a group. One is as I said, we did Lambda.js for ECMAScript 3. Now we're doing it for ECMAScript 5 and using the Conformance suite that's now part of the standard. So it's very nice. We have this sort of synergistic relationship. Type JavaScript I told you about with object types. We've been working for some time on something called Flapjacks, which is sort of a reactive programming framework on top of JavaScript. We started out all of this because we needed to do static analysis to do server-side intrusion detection. Because when a server sends programs down to a client, it's kind of, in the web world, it's kind of a hope, right? Not a guarantee that that's what's actually going to run. So we were able to extract a specification of what the client is supposed to do by looking at the code, and then randomize that code, because there's no reason I should send you and you the same code, because that lets you attack him, right? It lets you know what his code is. So we were able to randomize the code that different clients get. But to do the randomization, you need a sound analysis. And that was the thing that inspired all this JavaScript research, is we said we have no reason to believe our analysis is sound, especially because we were operating on the source language, which just has way too much noise in it. Like, plus, right? If I say plus, a quarter of the room starts to smile. Plus in JavaScript is actually a page long, right? And it's got all these weird cases. Yeah, exactly. So we came to conclude that we need a new approach, and that's what inspired all of this. So now we have a semantics for the DOM. It's appearing at Usenix web apps. And so the thing about the DOM is there's two parts of the DOM. There's a tree. That's just a damn tree. Tree's not that interesting. But what is interesting about it is that the DOM is where JavaScript is inert without the DOM. It just sits there on a page. It doesn't do anything for the most part until an event comes in. So to really understand the semantics of JavaScript on a page, you have to understand the semantics of event dispatch, which basically there's something called a capture phase, a target phase, and a bubble phase. So there's sort of a three-phase algorithm, and you're allowed to escape at any point. So the right way to think about the DOM is it's a great big control operator. That's what it is. Okay? And so JavaScript and the DOM are two control operators that sort of are mutually recursive. And so now we have a semantics that actually explains what the DOM is doing and lays this all out in a mechanized semantics that people can use. And we've started to use it for some other tasks. We're working with Google on capabilities for authentication and sharing, basically turning capabilities into something that works with modern web frameworks. I believe this is due to go into App Engine any day now. And we also have some static reasoning for capabilities built on top of App Engine. So that's sort of an outreach story there. We're right now looking a lot at browser extensions. Here's a funny thing about browsers. So browsers are extensible, right? How many of you use, well, I shouldn't ask in this room. How many of you use Firefox? Okay. Oh, well, okay. There you go. And so Firefox has extensions, right? And the whole point of extensions is they have extensive privileges, unlike the JavaScript inside the page, because they're allowed to change the behavior. Well, Firefox also has private browsing mode. What's the interaction between the two? It turns out, extensions came first. So Firefox said, oh, you can do whatever you want. Your private browsing mode, do whatever you want. They said, well, that's not a good idea. So now they put a bit in the API that you can look up if you wish, that asks, am I in private browsing mode? And then potentially change your behavior or not. And there's a manual review process for it. So Chrome said, well, this is crazy. This is no way to build a system. So Chrome automatically turns all extensions off in private browsing mode, which sounds like a great default. And it's a wise default. But there are two problems with it. First is you can turn them back on, and there's no advice that tells you whether you should turn it back on, whether it's safe or unsafe to turn it back on. The other problem is the most common extensions are things like AdBlock and NoScript, which people use to protect their privacy. So those are the things that have just been turned off by Chrome. Right? So the point is it's a subtle thing, this interaction. It's not an obvious right default, even though there's maybe a slightly safer default. So what we're doing now is analyzing browser extensions for whether they violate private browsing mode or not, and think about ways to just scale it to other forms of modality as well. And that's another type JavaScript story, as you might guess. Right? That's a kind of sandboxing argument, essentially. We're also working on, now that we've built 3-4 type systems, we've realized that there's actually a pattern to all of them. It's something that we call progressive types. The type soundness theorem for the ADSafe work is a little weird because we don't actually have, we have preservation, but our progress statement is really quite weak. And that's because termination here is not an observable channel, and it's anyway not a channel we were told to worry about. So terminating a program is okay. So there's a trade-off when you take a legacy piece of code and try to bring it into a type system, which is you can make a programmer do a little work or a lot of work. And if you actually have to be able to type every application and make sure that you know the precise type of every field in every object so that when you try to use it in application position, it's going to work out, that's a huge annotation burden. So we resolve it to some extent by actually running the program and recording types and giving that as an initial hypothesis to the programmer. But it's still a fair bit of work for a programmer. And maybe they don't need the full guarantee that the type soundness theorem comes with. So progressive types is a way of saying you can select in a checkbox precisely which which exceptions you do not want to see at runtime, right? Now, in a language like Haskell, it doesn't really make sense because there's a whole world of exceptions that were never listed anywhere because you have a typed language. But in Python and in Racket and in JavaScript and so on, we know what the runtime exceptions are, and some of them are the ones that are being prevented statically. So you could choose, I'm willing to accept more of these runtime exceptions in return for a lower annotation overhead to get the program through the type system, and then hopefully ratchet it up as you go along. So it's a dual kind of gradual typing, right? You ratchet up the guarantee rather than the places where you put the annotations. So that's something we're working out. And the last thing is, this whole JavaScript thing is complete nonsense. Of course, nobody should be programming in it. So we've been working for some years on a system called Alchemy, which is taking Alloy specifications. Alloy is a relational modeling language from Daniel Jackson's group. Taking Alloy specifications and automatically converting them to programs. And there's a bunch of interesting things there that I won't get into here. But anyway, that's where we are. The other experiment we're doing as a research group is blogging. We now try to blog once a month. We take one result and try to explain it in a reasonably accessible way. They get a few thousand readers, so that's something, though they don't stay on the site for very long. Some of you may have heard of What? What? Anyone remember? Yeah, okay, so the hackers in the room. This was a very entertaining presentation by a programmer that, how would you describe it, sort of is scripting languages for people who don't realize how wonderful they are. Hi, yes, here I am. Yes, as a matter of fact, speaking of intrusions. It's basically, it's a very entertaining blog. Look for WAT ? Just search in your favorite search engine, and it's 5 minutes of your life that you'll be amused. And so what we did was we took all the JavaScript portions of the What video, and ran each of them through the semantics that we have. We basically said, hey, these are test suites. More test suites are better. So we ran them through the semantics and showed that our semantics can predict what the What video says will happen, except in a handful of cases because there's an undefinedness about the top-level semantics of JavaScript, and we found a bug in Firefox as a result. So it's good. We like random stuff off the web is all good. So anyway, that's where we are, and that's the collection of stuff we're working on. Okay? And I'm happy to take questions. Those who need to leave, please leave. But thank you for coming.
What's question mark is not sufficiently.
What's his name? Gary. Tell you what, search for S5:what. Look for the blog post, and then there's a link on the blog post. No, that's our blog post about it, so that should work. And then that'll get you to our blog post, and from there you can go to the actual video. There was something we put off in the middle of the talk. Occurrence typing, yeah, spines, yeah. So there's occurrence typing in Sam Tobin-Hochstadt style is really written for very functional programs where you always write ifs and nest ifs nicely. It turns out that at some places like Mozilla, the house style is actually opposes doing that. The house style is instead you do a conditional, you do a type discrimination, you do something, and you either throw an exception or return, and then return back to sort of the left column. Right? They want you to have your spine as straight as possible. So you do all of sort of your exceptional behavior, and then it actually sort of improves the readability of the code because you can just read the primary behavior at the end of this collection of ifs and returns. Right? And Sam style would never be able to type that because that sort of is opposed to the style that he wants to handle. right? So in contrast, we allow you to straighten out your spine. So because in SAMs, the spine sort of goes like this. So I call it chiropraxy, right? So we straighten out the spine because these returns are something that the flow analysis knows how to handle, does the type discrimination, and when you get to the mainline piece of code, you can say, that is the main behavior of the function, and all the types have now been properly refined. And there's actually a fair number of interesting programs that use this kind of style. For example, every time you have optional arguments, you will find code that says, if the third argument equals undefined, do something, either return or patch it to be the correct value, right? Or patch it to be, like splice, right? I give you an array, I give you a start and an end point. If you leave off the end, it says the end if end equals undefined, end now equals array.length. So to look at end in the main body of the code, you have to reason about both control flow and state to know that it's type safe. But it is type safe. It absolutely is. That conditional was written there precisely to make end in the body be type safe. And we can handle that kind of thing because of our use of flow analysis. So that's the relationship between those two. Yeah. Other questions? Yes?
So Andrew sort of promised me I would feel better about JavaScript.
No, well, ask him. I didn't, yeah. Well, look, all right. So me personally, this is where my head is. Okay, this is where my heart is, certainly. But if you accept the fact that it's out there and half of it is a perfectly reasonable language, right? It's sort of like Scheme with like bad syntax. So what could be wrong with that? So if you accept that accept that there's a reasonable core, which there is in all of these languages, right? There is a reasonable core sitting in all these languages. Then what we're doing with our type system is basically making that reasonable core more immediately obvious to the developer, right? Instead of JavaScript, the good parts, which is this lovely little book, but it's, you have to read a whole book. Here's a type system that basically keeps you in the good parts. That seems like a perfectly reasonable thing to do. The other thing that as a programming language researcher that interests me a lot is this idea that somehow this associative array data structure seems to have some real value to it, right? People seem to like it a lot. It seems to be convenient for rapid software development in a way that like the list never really took off, right? So I don't know why that is, but it seems to be a very popular data structure. But if you look at what people are doing, if you study the code, they're using this associative data structure sometimes as an object, sometimes as a dictionary, sometimes as an array, and sometimes as some confused combination of all of those. Okay? The Google Docs bug is pretty amusing. So what Google Docs was doing was they created an object as a dictionary, and then they put every single word in the document inside that dictionary. Okay? So they reference it, so when you type search for words, they can use this hash table that's built into the associative array to tell you where the word is in the document and very rapidly show you all the highlights in the document. Okay? Sounds great, right? What could possibly be... No, it's a hash table, Simon. Oh, you would have built a hash table. They've given you a hash table.
It's kind of like using a hammer as a sword.
A hash table is a hash table. That's brilliant. What else would you do? But it turns out that it's actually a JavaScript object. JavaScript objects have a prototype field called __proto__, obviously. And if you type __proto___ in your Google Docs document, yeah, exactly. Locks up, and you can denial of service attack on somebody who's sharing the document. And of course the problem is the hack is it's almost as bad as the initial solution, right? You got to like put a prefix of some string in there, right? X before everything or something like that. So our type system will let you handle this kind of thing, of course, but it's just horrible, right? So it would be nice if we could try to extract some of those principles out, and that's what we're trying to do in the type system, is to say, look, this is an object that's being used as a this is an object that's being used as a that, so you can separate out these uses. But one of the things that does intrigue me is, so you want to start with this hacky thing, perhaps, or people seem to want to. You then grow your program into something that's well-typed and disciplined. But how does that sort of what about the loop? How do you tie the loop? Because now you're here, and you've lost your flexibility. How do you gain flexibility back such that you can, how do you weaken your program, right? You've hardened it. How do you soften it again so that you can re-harden it again? Maybe we don't need to. Maybe we do. I don't know. We don't know enough about this stuff. And my other side is I do a lot of empirical work with programming environments and things like that. And I want to start doing more empirical work with languages as well. Right? HCI on environments is obviously something we should be doing. We clearly, programming languages are human things, right? We should be doing HCI on languages much more than we have. It's very little good work in this area, and I think we should do more. So.
A silly question. Why did we use Redux for formalizing the semantics?
Why did we use Redux?
Why didn't you use Redux, or did you use Redux?
Oh, we did. So no. So in fact, the Lambda.js, we originally did it in Redux. The problem is the execution engine's just far too slow, so we end up writing the interpreter again. So we have used Redux, we've used OCaml, we've used Haskell, then we went back to OCaml, went back to Haskell, went back to Redux, and now I think we're back at Haskell. We can't find something that, there's lots of things that are sort of good and nothing that's good enough. Yeah. So, question, yeah.
Browser extension with a type checker built in, so I could run it in my web browser as I develop JavaScript code?
If we got like 50 people asked us for it, we'd build it overnight. We haven't had 50 people ask for it. In fact, there seems to be sort of types and the JavaScript culture don't seem to quite match up. So, yeah. You need 49 friends, yeah, and then we'll build it for you. Yeah.
So you mentioned you can't forbid communication between regions.
Yeah.
What's the potential threat? Given a program passes JSlint, what's the current threat?
What's the threat? Well, so one is collusion, but that seems like, okay, I mean, if you want to collude, you could have colluded offline, right? So what's the big deal? The bigger problem is you don't know what the nature of that communication is. If so I'm Farmville, and I happen to notice this other game company's widget is on the page, well, I could just go and like bombard them with junk messages that I know will cause them to crash, making that game, putting that game out of business. That's the bigger problem, right? Whereas if you went through ADSafe would say, wait a minute, you're Zynga, you're not supposed to be talking to this other company, what are you trying to do? And it could block it. So that's why you need the mediation. Does that make sense? Other questions? Okay, great. Thank you all for coming, and thank you for the questions.